very much.
Yes,
May I
please.
start? Okay. Thank you very much. Uh, Good morning. Today we try to. I will give a special lecture in front of you. It's about brief on control engineering and application. I think it's maybe a brief explanation about control system and some application related to what I did in my research. So I think I will not go in deep on theory, but we will go more on how we understand about the control engineering, and we will see where the application. Okay. I think Dr. already mentioned about my brief CV. So I will go directly on the definition, simple definition about control system. I think all of you already know about this, but I want to review this definition to understand more about what is control system. Maybe before, during this semester, you have already learned many things about control system, starting from basic and then ended with how to analyze and design a control system, simple control system. Okay. In We define control system. I think we know that control system is a system which provide a desired response by controlling the output, meaning that we are focused how we get a desired response from the system by add a controller for the system, because the system with their original condition maybe cannot meet the desired response, so we can add a controller to adjust the performance of the system. So why the definition of a control system is a system which provide the desired response by controlling the output. So we make sure the outputs can follow what we want from the system. So for example, we want to turn DC motor in 100 RPM. When using only a closed loop system without a controller, we only will get only maybe 90 RPM. It means that it's maybe uh, uh, the output can reach the set point, but maybe it reach the set point slowly, or sometime maybe he will give a high overshoot, and then very slow settling time, or maybe the steady set error may be quite big. So we need a controller we put before the plant to know, to encourage the plant to reach the output, or to reach the output, the actual output, reach the desired output we want.
I'm
So
sorry, Doctor.
yeah,
The slide still in the page number 1. From here we can see.
okay.
It's not go to the desired
Oh
slide.
no, okay, okay. Wait
All
a
right.
minute.
Okay.
You can see it. Okay, so not yet.
Still in slide number 1.
But wait a minute. I'm trying to. Is it? It's a number 3.
Yes. It's,
Okay.
all right. It's still moving. It's the slide is moving.
I'm trying to move to
Yes,
number
is
4.
it okay?
Is it okay? Okay. Okay. Thank you very much. Okay. This is the slide where I was talking before. It's about how we define a control system by uh, by uh, by using a block diagram and a sample. From the definition we made before, so we can see here we have a controller and then we have a plant, and then normally we will use not only open loop. I think mostly we will use a closed loop a block diagram by add feedback element here to adjust the output by controller. So we hope the desired output will follow the desired input, and then we can get a very very small error from the steady state error. So I think the concept how we try to control system to encourage the system to get the desired output. A simple example, like in the right, you can see a DC motor to above DC motor. We use a simple a concept of control here. It's only closed loop control, and then we can adjust the input by turn the potential, and then it will give a response, and then we will give a high input for the system, so the motor will turn faster. Okay. The diagram block will be we can see in the figure below how the speed control using Arduino, for example, and then output of the Arduino we inject to PWM, and then output of the PWM we go to DC motor, and then actual output of the motor is about motor speed. Then we give input, we compare the output with the speed command, and then we get an error, and then the error we will use to adjust the output of the motor. And then in where we put the controller we put inside the Arduino here, and then we can use any type of controller here to make the performance of the DC motors better and better, depend on our requirement. So okay, now after we understand about the concept of the principle of the control system, maybe we can review about element of the control system. We can see here, we can start from the left. We have a reference, and then we have a controller, and then we have a block actuator, and then there is a process there, and then when we have a feedback, we have a sensor to measure the output, the actual output, and then we give the signal to the back to compare with the reference. Is the actual output is the same or not with the reference or set point? So the difference is will be error. We call as actuating signal. So actuating signal is a signal that give to controller to give an action. For example, if the error high, means that the controller will will push to give its best performance, and then when the error is smaller, the control will work a little bit not fast as before when the error is quite big. So then output the controller normally we call as a control signal. Control signal is input for actuator. Here actuator we call as a correction element. We need to give more attention on the actuator, because actuator is element that give a correction of the process. For example, if we are trying to control temperature in a room, so what is the correction element? Correction elements normally a motor, a normal motor that we put in inside the room that control the room, and the actor can turn in the maximum speed or proportionally changing depending on the condition of the temperature. So correction element will active depend on the control signal. Means that we will give control signal maximum when the error is maximum. So actuation that give by actuator will depend on the condition of the output. So in this concept of control system, we understand that correction element plays the most significant role in controlling performance of a system. Meaning that in any application, actually we control actuator first before we control all the process. So in any application, we can see, we can check in internet, we can see any application for control system. Normally we control actuator, we control correction element, because correction element is the element that can influence the process, depend the output of the process. So when if you want to design a control system, meaning that mostly we will control actuator to control all the process of the system. Here also we can find internal disturbance normally is exists in the system, and also external disturbance. For example, if we control the condition of a room, I mean the temperature of room, temperature in the room will be influenced by outside temperature, meaning that outside temperature is external disturbance. The internal disturbance is a disturbance that can exist in the system, inside the system, that can be any equipment inside the system, or other parameters that can changing in the system. So this internal disturbance come from the internal of the system. So, okay, I think we already understand about this concept. Then based on this, I think we will normally define some main actuator in the control system. If we look at the application, we normally find a servo motor. Servo motor is a very popular actuator in many application system. And then industry, we can find easily a pneumatic system, then also hydraulic system, And then sometimes we put above part of the actuator that normally used in control system. However, valve normally is not an independent actuator, because above normally controlled by another actuator. For example, valve can be controlled by, the move of the valve can control by servo motor, sometimes controlled by pneumatic, sometimes controlled by hydraulic. Depend on depend on the characteristic of the application. For example, for simple things, normally a servo motor can handle the valve, but for high power application, for example, maybe we need hydraulic to move the valve. Okay. So normally an independent actuator we use in control system, normally servo valve, pneumatic or hydraulic. I think DC motor sometimes, but normally for control, normally we use a servo motor. We can see here some application for the actuator. For example, a servo motor we can find in a robotic system. Every joint in the motor we put in the robotic, we put a motor there. And then also in pneumatic, in robotic, we can find a pneumatic system. But sometimes we also find hydraulic here in the robotic system. Independent the function of the robot. In manufacturing robotic, normally we use a pneumatic or hydraulic. And then the last one for hydraulic, maybe we can see wind turbine structure. In wind turbine structure, we can find a pitch control. Pitch control is a control that used to adjust the blade of the wind turbine, and then to adjust the blade, or sometimes we also find in to adjust yield of the wind turbine, we can see hydraulic in as the equipment. It depends on the how big the size of the wind turbine. Normally for the bike, normally for the big size of wind turbine, normally we use hydraulic. Okay, because to turn the blade, it will be very hard and need more power actuator to turn the blade. So we apply hydraulic for pitch control or yield control wind turbine. So it's is the example clearly that in any application we can see actuator is the main element we need to control before we control all the process of the control system. Okay, now we might need to ask why we need a control system. In any control process, maybe we only do three things. First, we make sure that transfer response performance of the system is better, meaning that overshoots, a slower overshoot, maybe a lower overshoot, or maybe without overshoot, then faster settling time, and then we need fast rest time, for example. I think it's three main parameters of transient response we need to adjust before we want to get the best performance from a system. And then the second is accurate tracking. Accurate tracking means that we have to find as small as possible steady state error. Okay. Normally, when we look at the response of the system, after we found the best trend response for the system, normally we will adjust is the steady state error is enough, or we need to get more a smaller steady state error for the system. For example, when we trying to design a controller or compensator, for example, if we only want to adjust or to find a better transient response, maybe we only use a lead compensator. But when we want a smaller steady state error, we will add lag compensator for the system to get a better steady state error for the system. And then the last one is we have to ensure that stability of the system is okay. Meaning that if the system's running and then we find or we meet the change or parameter of the system, and then or we find a nonlinearity in the system, or there is a disturbance, for example, the system still remains stable, then the controller must be guarantee the stability. Even the stability has a limited, I mean there is a boundary for the stability insurance, but a controller must be ensure the stability of the system. I mean the system is must be stable when the nonlinearity, uncertainty, or disturbance exists in the system. So if we design a control system, means that this three point must be found, and then we can get the best response for the system. We can get the best performance for the system if these three parameters can meet, and then I think any controller we apply for the system, we have to meet all these other things. But sometimes we have also condition where we not need to apply one of them because we think that the parameters already enough. For example, maybe we trying a lead compensator for the system. So only we find the best transient response for the system. Then we look at the steady state error of the system, or tracking accurate tracking error for the system is already good enough. Then we not need to design for the to adjust the steady state of the system. Then we only continue for stability, because stability normally need to ensure when the system get or face some disturbance or uncertainties during the system is running. For example, for a highly linear system, such as hydraulic system. Hydraulic system is a very highly nonlinear system, and then when the system is running, and then during the system running, sometimes some parameters is changing, or we found some linearities there. For example, friction or another else. So maybe the performance of the system will be changing. So normally will be lower. So we have to maintain the condition of the system, and then maybe the system is not stable and changing from the move from the steady state condition to somewhere. So the error will be not. The system will get a problem, and then if we apply the system to the to an application, we will get trouble for the application. Okay. What are the from the last slide? Maybe we can think that what is the challenge for the control system? First is nonlinearities. Nonlinearities is the main problem for the system, because sometimes we face a system, for example, hydraulic system. Hydraulic system normally highly nonlinear system, because some parameters they're changing, and then maybe we can find a friction, and then when we run the hydraulic systems in a certain time, maybe the condition of the oil will be changing, so they cannot push the piston as good as before. So meaning that the stiffness of the hydraulic system of the piston will be changing. So is the challenge for the control designer to meet a solution for nonlinearities problem. The second one is a system parameter variation. Some parameters in the system will be changing, so control system need to has a formulation to solve this problem, to maintain the performance of the system. Then sometimes we also find unmodeled dynamics, because when a system is running, maybe we cannot identify some dynamics in the system, and this dynamics we call as unmodeled dynamics. Then the last one is disturbance. Disturbance can be internal or external disturbance. Disturbance also very influence to the performance of the system, so we have to fix the disturbance. And then in the control theory, we have found some formulas, some concept that can cancel out the disturbance, and then when the system face the disturbance, they cannot affect by the disturbance. Okay, I will show you later on about how we cancel out the disturbance, and such that the disturbance is not affect to the performance of the system. Okay, what is the main issue in control system? The first is about modeling. Why modeling? Modeling means that we try to transform the real model to the real system to a model, and sometimes we get problem during modeling, meaning that if it's a simple system, it's still no problem, but when the system is a highly nonlinear system, so we have a problem for the model. Why? Because when we trying to compare result of the real system and the model of the system, maybe we can find a large difference between both of them, because maybe some parameters or some linearities or other uncertainties and model dynamics cannot we hasn't put to the model. So we have to create a very precision model for the system to make sure that every part of the system already inside our model. Meaning that if we want to get a base model, so we have to put we have to add some parameters to the model. So meaning that the model will not only a linear model, maybe it will be a nonlinear model. For example, we can try to a simple actuator, for example, a servo motor. Maybe we can try to model the motor, and then we try to run the motor in a closed loop system, and then now we compare the system with the same input. Then we look at the output. We compare the output between the real system and then when we run by model. For simple system, maybe the difference is not too big, but for the system that influenced by nonlinearity or uncertainty and so on, maybe the difference will be very big. So during the modeling, maybe we need to model system in a linear model to get the best model for the system. I done it many times in experiment, also in simulation by MATLAB. For example, DC motor and then pneumatic system or hydraulic system. I'm trying to compare the results. For the DC motor, the difference is not too big, but for the pneumatic and hydraulic system, the difference between the output of the model and the on the real pneumatic or hydraulic, the difference very big, because maybe there is a simplification in the model, and then we need to do to develop our model and put some nullities or uncertainties inside the model. Okay. Another thing is about response analysis, because we want to design a system, we have to start from modeling, and then we continue to simulate the model in MATLAB, or trying to apply to the system, and then we find a response, and the response we have to analyze the response based on its stability, and then its transition response and steady state error. Based on the response, we can design a suitable control design for the system, and we can decide we will use a linear controller or we will use a nonlinear controller. Normally, if we use a linear model, we use a linear controller, but if we develop a nonlinear model, normally we will use a nonlinear controller for the system. Okay, I will continue with this. It's about type control in control system. Normally, we find a linear control. Maybe you have already learned about PID control. Maybe next semester, I think we you will continue with pole placement, LQR, LQG, maybe another type of linear control. In nonlinear control, maybe it's advanced control we normally learn. It's about hash infinity. It's only example, okay? There is a sliding mode control. There is a backstepping, and so on. And then intelligent control, normally we find a fuzzy control. And then there is a neural network. And then sometimes we combine all together fuzzy logic and neural network. For example, UNFIS, for example, that is we call as a hybrid intelligent control. Sometimes we combine between linear control and intelligent control, or sometimes we combine between nonlinear control and intelligent control. Another part, normally we also apply adaptive control. Adaptive control means that our controller, it can be linear or nonlinear control. The controller will be adapt to the condition of the system more, not only from the error, but also another parameter. So the system will be improve the performance of the system better than only we use on nonlinear control. For example, sometimes we combine, for example, fuzzy PID controller with fuzzy control, or PID control with narrow network, or combine between sliding mode control with fuzzy, sliding mode control with narrow network, or backstepping with fuzzy or something. And this combination can make the controller, our control scheme will be better to get the best performance, to give the best performance for a system. So it's a normally controller we can found in any application, but this type of controller always changing and developed based on the research done by by researchers around the world, depend on the application. Okay, this is main part that I want to share on you is how we design a control system. We normally work not only model the system and then simulate in MATLAB, but sometimes we need to apply the proposed control to the real system. So why we need to understand the step in control system design. I did many times in my research, because my research normally not only based on the model, and then I try to create a control design, a control scheme for the model, but also trying to apply the proposed control to the real system. We can see here, we can start from, normally we can start from the modeling, how we model the system from its physical system. And then we can find two type of modeling there. You have done it, I think. We can find the model in transfer function form. And then also we can make it in state space model. It depends on the function of the, it depends on what type of controller you want to apply. Maybe for the simple things, maybe we can use a transfer function model, because maybe we not need to adjust some parameters from the transfer function. Normally, transfer function base is a nonlinear model. But when we need if we need to apply a nonlinear control for the system, maybe we will apply a state-based model for the system. So how we model the system is depend what type of control we want to apply for the system. Okay, why we apply state-based model for nonlinear system? Because state space can accommodate the change on the system. For example, we can put uncertainties there, and then we can put a disturbance or some linearities in the systems easier compared we use a transfer function. So for advanced control, normally we use a state space model. So if we're trying, for example, if we're trying to design a control system for robotic system, for example, we normally use a state space model, and then we can see that the model can be in 10 or more than 10 states. Yeah, meaning that the order of the system is already very high. It depends how many uncertainties or non-linearities we put on the model. And then sometimes also we can simplify the model in transfer function, or we can change or we transfer the type of the model from state space to transfer function, or we can transform from transfer function to state space. Okay. After we find the model, transfer function or state space model, meaning that we need to simulate the system. Model simulation to obtain output response, and then we can do some analytical analysis for the response of the system to decide what type of control we want to apply for the system. So based on the simulation on the model, we can see if the system is nonlinear. I mean, we can see from the parameters there, stability or transient response, or depend on the steady state error. We can decide is the control system for the best control system for the system is using non-linear controller or linear controller. So this analysis is very important for us to decide the controller. So for this part, analyze the output of the output response from the model. We can see the transient response, stability, or error steady state of the system. We can use it in time domain or frequency domain. I think in the mid of the semester you already done this, how to analyze the response of the system based on time domain or frequency domain. You can use a bot plot or a locus or something, and then depend on the type of response you analyze. Okay. After this, what we want to do is we design a controller to improve the system based on three parameters: transient, stability, and error steady state. So during the analysis, maybe we can see that maybe settling time only maybe 4 seconds. We want to improve to 2 seconds, or maybe during the analysis we find that stability of the system is quite weak. For example, it's close to 0. Almost it can be become unstable when we adjust or we got some disturbance to the system. So we make sure that the stability of the system can be guaranteed, and then errors to the state system also can be reduced from the previous value. So meaning that design control is designed based the condition of the system during analyze that made to output or response. Okay. After we design the controller, maybe I think you have done it for PID controller. Then we try to simulate the controller to the system. If we see that the simulation result is good enough, I mean that the parameter, the controller that we use in the system is good enough to adjust to improve the transient stability of our steady state system, we can decide to apply the controller to the real system. The problem is, what about if the control system is not as good as we expect? So we need to adjust the controller to better and better. This step also we can do during we model the system. For example, when we found a model from the system, and then we try to simulate the model in MATLAB, and then we're trying to validate the model response with a response from the real system, and then we compare it together, and when there is the difference between both, so we can do remodeling for the system, meaning that we have to remodel the system to make sure that the output of the real system is close to the output of the model. Why is need to do? Because if the difference between the real output of the real system and the output of the model is the difference quite big, we have a problem when we apply to the real controller. Meaning that any, I mean, if we found the good result when the controller we apply to the model, we will find the difference on the output when we apply the controller to the real system. So why, before we design a controller, we have to compare between the output of the model and output of the real system. But if we don't do this, I mean, we not need to apply the controller to the real system. I think it's not a big problem. So we can go ahead. Maybe we go for a simple model. For example, maybe sometime, for example, the system is normally a five order system, and then we reduce the system become 3 order system, and then we run it in simulation, and we know that a big problem with a transient, and then stability is okay, and then we need a little improvement in the steady state error, and then we design a controller, and then after design controller we simulate it, and then we can find a better result. I think it's easier if we not apply the proposed control to the real system. So why? The best things in control system is when we apply the proposed control design to the real system. That's the challenge. This is a big challenge for control system designer, because if we go only to simulate the model and design a controller for the model, and then we simulate it and the result is look good, and then it's enough. But it need to verify, is it the controller is good enough for the real system or not. So the best thing is how we apply the proposed control both for the real system and for the model and for the real system, because we are design a controller not only for simulation, but we need and we make sure that our proposed control can apply for the real system. For example, we apply to the DC motor. We 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 did only in simulation without verification on the real system. Maybe when we apply the model to the real system, we will find a big difference between the response will be different compared to what we found in the simulation. For control engineer, I think it's a big challenge how we can apply our control design to a real system. So in research, maybe sometimes I'm not too yeah, I'm cannot sure is it the result is okay or not when the a researcher only apply to the model, but it will be very will be make the, for example, when I'm reviewing a journal, I will try to look at is it the control system is apply also in the real system or not. If the control only in simulation, I'm not sure is it true or not. So if they give verification that the controller already applied to the real system, even the result is not really the same, but and there is also a small difference, it is still okay to validate that the control is good. Okay, I will try to give some simple application at the end of my presentation today, our lecture today, before we did a question and answer. It's a simple one. I think it's a normal one we found in experimental work or in lab work. How we control a DC motor using a position sensor here. How motor can control based on the position of the sensor. Okay. If you want to put a controller, we can put before the DC motor here. It's only look like a closed loop control motor system. We can see also in the figure below is also a speed control for the system. We make sure that the motor can run in the same RPM to make sure that conveyor can run in the precision to make sure that it can capture the thing in the black one here in a precise position. This is a type of simple controller. We can put a system control here. It can be PID or something else to make sure that the motor is moving in stable condition, meaning that with as small as error, steady state error, and then small overshoot, and set a fast settling time, and fast rise time. Okay. The next one is about level control. Water level control also we can find in many application industry or in our house. Okay. We can see here what is main equipment here. The main equipment is here is a valve, meaning that to control a level of the water, we need to control the valve. Okay, we need to control the valve based on the actual level of the water inside the tank. Another one is also about valve. It's about heat control system. We can find in industry, normally in process control, how we control the actuator. This is a steam control valve here. We control the actuator precisely to make sure that the water inside the tank is remain the same by maintain the condition of the actuator. But sometimes the tank will influence by outside condition. For example, the temperature outside. I mean, temperature during the day or at night, it will be different, influence the condition of the water. So the actuator can control to follow the change of the condition of the weather outside the tank. So it's any application can be found here, can be applied here to make sure that the water inside the tanks is constant. Okay, this is a home heating control. I think another simple application here. We look at here. What type of actuator we control? The type of actuator we control is a valve, almost the same with the previous example. We trying to control the valve to make sure that sensor inside, heat temperature inside the room is depend on our requirement. For example, if you want only 20 degrees Celsius, so heater inside the heater will be working to make sure that temperature is meet the requirement. Okay. What the actuator? Yeah, what I'm saying before, the actuator is a valve. Okay. Now it's about cruise control system. Cruise control system is about how we make sure that the distance between one car to another car is remain the same, and they will give a sign when the distance is changing. So to control this condition, we need to control above for fuel flow. So the speed of the car will be depend on fuel flow. So to make sure the fuel flow is controllable, so above of the fuel flow will be controlled by a controller. So the effect of the when we control the fuel, so the vehicle speed will be can be controlled, and the speed will be remain, and that effect to the distance between one car to the distance with the another car in front or behind the car. Okay, this is a simple one. I'm trying to give you an example for some research here. I will go faster here. I did it in during my PhD. It's about how to control a hydraulic system precisely by using this test bed. We can see here we have to move the piston precisely depend on the reference. Now at the end of the piston, we also give extra disturbance here, external disturbance here. We make a controller to make sure that even the external disturbance exists, yeah, the response of the piston or the displacement that reached by the piston is not changing. So we're trying to compare between with and without external disturbance. We make sure that the piston will still can move on the reference distance in the same position, and we can control the condition of the system by some sensor here. We use a accelerometer sensor here. We have LVDT sensor, and then we have also a pressure sensor here in both of the hose of the cylinder. This is a test bed for to test the system when we apply a controller for the system to make sure the nonlinearity and external disturbance or other any other condition is not impact to the performance of the hydraulic. Okay, it's only a diagram for the previous figure. And then what we want to do in the research, the first is how to formulate complex mathematical formulation. I'm trying to follow what we explained before. And then the second one, how to propose a new control strategy that integrate adaptive, robust SMC and NDO is adaptive control. And then we try not only design a controller and apply to a model, but also apply to the real implementation. Okay, we try to do a modeling for the system based on condition of the system and a formulation that found in many books, and then we have found a model for the system. We're trying to define in 3 states here, x1 dot, x2 dot, and strict dot here, and put some nullities or uncertainties inside the system. Then the system, the model of the system we call as a nonlinear model system for electrohydraulic system. And then we put here nonlinear dynamics for the model here in the third state, meaning that we ensure that the model is a nonlinear. Okay, this is a result of the simulation and a real condition we're trying to apply. Yeah, this is the reference, and then it is open loop. Yeah, open loop test we did on the model. You can see here XP experiment compared to XP with simulation. So we can see here from the response between the simulation on the model, on experiment on the real system with the same input, the result is almost the same. Meaning that our modeling that's true, then we can continue to design a controller for the system. This is the way one step that we have to do when we want to apply the proposed control to the real system. So we start to make sure the model is almost the same with the response of the real system. Okay, this is the proposed control design here. We can see here is the system is nonlinear. We have already defined or model the system in nonlinear system model, and then we trying to design a nonlinear control for the system, and then we put nonlinear disturbance observer for the system. From the condition of the system, we can see here nonlinear control of the system will influenced by the condition of a nonlinear model. Meaning that is a part of adaptation that has by the scheme of the controller. Okay, what I find from the system, we can see here when we apply to when we apply to the proposed control to the system, we can see here we can see between PID and SMC here. PID control is much better than SMC is much better than PID control to solve the problem of the system. Meaning that SMC or nonlinear control like SMC is better to give a response compared to PID controller. Okay, this is we can compare. This is a simulation, and this is an experiment. This is almost the same. With the same input, we can find almost equal result between simulation and experiment. This is verified that when we apply both to the model or real system, the proposed control give the same response, almost the same response, meaning that the model is true, and then the control system is true. So meaning that the proposed control is verified by experimentally. Okay. Okay. The second one is how to control a governor system in microhydro system. is normally how we control water flow in governor control. We make sure that the generator is can turn in the same condition to find to find a constant frequency for the system, even when the load changes. So when the load changes, normally in micro hydro system, the governor the generator will be slower. So the governor makes sure that when the governor when generator getting slower, so the governor will open the water bigger to compensate the change of the generator, to make sure the generators turning return to the its normal frequency. Okay, to make sure this condition, we found an actuator to make sure that the water is we need an actuator to make sure the water is follow the change of the generator. We use a hydraulic system here. Sometimes we apply a servo control here to open and close or professionally change the what we call a gate opening of the micro hydro system. Okay. What we do is we apply to use fuzzy PID here. By using this concept, we can find a better condition of the system. We can see clearly in we compare the frequency. If we apply flow control here, we can see we will find a better result with fuzzy PI here. Okay, another things is another examples. I'm trying to apply SMC PID to micro hydro frequency control here. And the same object. If the second example, I'm using fuzzy PID control. In the third example, I'm trying to apply SMC PID here to control the governor of the system. Another thing is about wind turbine. Wind turbine is a problem when the direction or speed of the wind is changing. So we have to control. In this example, we're trying to control the blade of the wind turbine. If the speed of the wind is changing, so we can control using a pitch control. So here we apply SMC here to make sure the actuator in the pitch control of wind turbine can work precisely depend on the change of wind speed. What type of actuator using here is a hydraulic system, but sometimes in any application we also find servo motor as actuator for the pitch control. In the diagram below, we using backstepping is also a nonlinear control for the actuator. This type of actuator is this type of backstepping control also give a very good result compared to PID. I'm so sorry, in this research I don't put a comparison of the results here between a backstepping controller and normal or simple control like PID. Another one is active suspension system. Is system suspension in a car. When we change the load and then route profile is changing, we combine SMC PID there as a controller with BET algorithm. BET algorithm is optimization computation that we use to find the best parameter for SMC PID to get the best performance for the SMC PID. So we optimize the parameters that we give to SMC PID to get the best performance for the system. Even the load and route profile is changing. Okay, this another things. A simple one is a BLDC and servo motor. The first one is a BLDC. We're trying to control BLDC motor here by using SMC PID, and then in the second diagram there, we're trying to control servo motor using PID SMC. In this application, for example, in case control DC motor, servo motor here, we apply this servo motor to give much accurate positioning to control what we call PP solar photovoltaic, yeah, to get the best position to get to the sun. I mean, it's like a sun tracking for we call it solar tracking. Yeah, solar tracking into condition I mean, we use to axis control for sun tracking. Yeah, depend on to the change of position of the sun. Okay, okay, does it maybe is too long for you because I want to say or brief concept in design concept in control system and some application maybe will give you an overview regarding the control engineering system. Thank you very much. Maybe we can continue for answer and question and answer.
Thank you so much, Dr. Zulfatman, for the very clear and informative special lecture about the control system engineering. Thanks so much. Do you have any question? You can ask through the microphone and also via the chat box. A student did a project in order to apply controller to a system. However, the project only based on the simulation only. So I'm really happy that this must stress out about the actuator. The importance of the actuator in order to do the correction element, is it?
Yeah.
In control system. So, so this is very, very useful information to student. All right. How is it? Is there any question regarding on the lecture or whatever that you have in your mind regarding to the control engineering? There is a question in the chat box. Is learning control?
Yeah, it's a learning control. Yeah. Okay. I'm trying to answer it.
All right. Thank you.
I think it's not. Depend on your. Dalam bahasa Melayu kita sebut bergantung niat. Ya. Yeah. If we want to learn it, I think we can do it. Yeah. I start from my undergraduate. I'm dealing with control system from my undergraduate and continue in master and then in PhD level, also doing in control system. I'm trying to love it, and then I find the beauty of control system when I took my PhD, because during my PhD, finally I find that uh, any formulation in control system, even it's hard to calculate or to design, actually is can apply to the real system. That's the beauty I found in control system, because during my undergraduate also maybe the same opinion with you. It's hard, everything about calculation, about mathematics, and so on. But when we try understand easily and we try to apply, I think, yeah, at the end I see the control system is not so hard. Okay, and then I think during the undergraduate, I think you can start for a simple experiment for the system. Okay, that you will find and uh, you can conclude at the end. I think control system is not as hard as I'm thinking. That's it. So because yeah, mostly in undergraduate we not much experiment. We not deal much on experiment. So we are thinking control system only calculation or formulation proofing or something. But when we try uh, to to do an experiment and make it what I give guidance in the slide, I think it will be okay for you. Okay, I'm so sorry. I'm my English not so good as Dr. Hazriza. Okay.
Thank you so much for the answer, Dr. Zulfatman. Actually, I'm agreed with the answer. I have the similar experience with Dr. Zulfatman regarding the beauty of the control engineering itself. Thank you, Hanis, for the question. There is another question from Saif Hassan. How is it employed, or can we employ the control system to set usage limits instead of reducing the error rate?
Okay. Maybe I haven't get the point.
Maybe, Saif Hassan, you can elaborate more regarding to the question.
Okay, I'm trying to understand the question.
Since they set usage limits instead of... Oh, so it means that you have some limitation of the source. So is it you want to make sure the usage of the source is not over the limit?
Okay.
Yes.
I'm trying to answer. Maybe sometime uh, we have. I think the limit is depend on the hardware. Okay, not on the software. So we need to work to purify the design not only in simulation but also in experiment. So we can see that limit of the system. Okay, so every system is every system has his boundaries. The boundaries is normally we call as uh, uh, I forget the term, but I, we can explain that the limitation of the I mean every system has their limitation. That's it. Okay. to find the limitation of the system, we can try some experimental for the system. I'm not sure about the term. It's about a frequency, natural frequency. Okay, we were talking about natural frequency. Every system has their own natural frequency, so we have to check experimentally the limitation of the system before we push the system to by controller to get its limit. Okay, I think that the answer that I can give to for the question.
All right, thank you. So is there any question regarding, thank you Saif Hassan for the question also. And then, is there any question from the student? While we're waiting, I have a question to Dr. Zulfatman regarding, based on your experience when during the experiment, what is the most crucial or critical part or difficult part to apply the control system to the experiment?
Okay. Thank you, Dr. Asriza. The most difficult part, the first one is in modeling part. Okay, in modeling part, because we can sometimes simplify the model, but when we compare to the real system, it will be different. So I think if we want to apply our control design to a real system, we have to start from to confirm that our model is close to the real system. Even it's not easy, but we try to as close as possible to the response of the condition of the real system. Okay, even we put the anomalies or something, maybe it's not only maybe in one term. Maybe we put one term and then we try again. Maybe we can maybe more than 3 times before we meet the best model for our system. I did it in my research, and normally I find the best model for the system is after I modeled about 5 times or more. Okay. And then when the model is the output of the model is equal to the real system or close to the real system, I think it will be easier for us to apply any type of controller.
All right, thank you for the answer. So it means that the modeling part is the most difficult part, is it, in order to compare with the simulation with the real hardware implementation. Okay, is there any question from student? So if not, so maybe we can end this session with the photo session. Is it okay, Doctor?
It's okay.
Okay, so hopefully the students, can you please on your camera? So maybe we can have a photo session. All right. So I'm getting ready. So new. Okay, anyone would like to turn on your camera? Okay, so 1, 2, 3. And another shot. Okay, get ready. I need to close it first. All right. Okay, get ready. 1, 2, 3. Okay. And before we end the session, I would like to thanks again to Dr. Zulfatman because willing to spend his time in order to give more knowledge to UNIMED student regarding to the basic principles in control engineering and also the application of control engineering in the industry. Thank you so much from us.
Okay. I
And
am
then
also
and then
attending
hopefully,
the invitation.
all right.
I'm so sorry if during the deliver the lecture maybe quite not clear in English. I'm so sorry for that.
For me, it's
Hopefully,
really clear about it. Okay. And also thanks to all the participants who joined this session for today. And hopefully, maybe this is not last time we meet together, Dr. Zul, Fatman. Maybe in the future we can have some kind of this session, and also maybe we can have some collaboration
Inshallah.
regarding of the research in contention, inshallah. All right. Thank you so much for your time again. Assalamualaikum and have a good day to you all. Thank you.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much.
Thank you so much, doctor.